Hello everybody, I welcome you all to NCAS Geology class. In my previous lecture, I have already discussed about the ancient methods of the determination of age of the earth. Now, I will discuss about the modern method. And this method is based upon the discovery of radioactivity. After discovery of radioactivity, the determination of age of rocks have been possible, and on that basis the age of the earth has been estimated. So let us discuss this method. All the calculations of the age of the earth as described earlier in ancient methods relating to the age of the earth, they are all based upon imperfections and speculations, and hence cannot be accepted. The discovery of radioactivity has brought new and apparently precise concept of measuring the age of the earth. So radioactivity consists of spontaneous disintegration of nuclei of unstable elements of rocks of the earth and their transformation to stable daughter elements. The disintegration involves emission of alpha, beta particles and gamma radiations. The basic principle of radioactivity decay is that radioactive parent element decays into stable daughter element at constant rate without being affected by change in temperature, pressure and environmental conditions. This is the key factor. The decay is expressed in terms of half-life period. That is, a time period during which a parent element is reduced to half of its mass with formation of other half as its stable daughter element. So, the parent elements which are radioactive, they undergo decay and they undergo decay at a very constant rate, and the time period during which its mass is reduced to its half is called as the half-life period of the element, and it is a constant fact, constant time. Mathematically, this half-life period, this T half means half-life period, is expressed as 0.693 by lambda. Lambda is the decay constant and it is constant for a particular element. It varies from element to element. And accordingly, the half-life period of different elements have different time periods as they have different decay constants. And the age of the earth is calculated by using the formula T, that is the age of the earth is 1 by lambda log d minus d0 by n plus 1, where d is the daughter element, d0 is the D is the total daughter element or the daughter element originally present in rock, that is D0 plus the number of daughter elements produced by decay. So D refers to the total daughter elements that is produced by decay and the daughter elements initially present in the rock, and n is the number of parent elements remaining after the time t. So this is the formula which is used to determine the age of the earth. Now let us derive these formulas common and discuss, and we will discuss on the common problems related to the determination of the age of the rocks. According to Rutherford, the rate of decay of radioactive nuclide at any instant is proportional to the number of atoms in the nuclide remaining at that instant. So rate of decay is always proportional to the number of parent nuclei remaining at that instant. This is according to Rutherford. If the number of atoms remaining at time t is n, the mathematical expression for rate of decay will be dn by dt, which is a first order reaction, and it can be written as minus dn by dt varies directly with the number of parent elements. The negative sign has been introduced because n decreases with time. With the decay, the number of n decreases. That's why minus dn by dt varies directly n, or minus dn by dt is equal to lambda n, where lambda is the decay constant, which is expressed in units as reciprocal of time. So minus this is the decay rate. dn by dt minus dn by dt is equal to lambda n. Every radioactive decay scheme has its own characteristic numerical value of lambda. So lambda varies from element to element, which is not affected by temperature, pressure, or chemical changes involving the isotope. The constant rate of radioactive decay over geologic time is the fundamental premise of age rating by radioactive isotopes. So we have got minus dn by dt is equal to lambda n, or minus dn by n will be equal to lambda dt. If we integrate it, we will get minus log n is equal to lambda t plus integration constant. If we take t is equal to 0, then minus log n 0 is equal to integration constant. Substituting this in the value of the integration, substituting this value of integration constant in equation 2, this is the equation 2, we get minus log n is equal to lambda t minus log n 0, and analyzing it, we finally get n is equal to n0 e to the power minus lambda t, which is equation 3. This is the basic equation where n is the number of parent elements remaining after time t, n0 is the original number of elements in the number of parent elements, then t is the time passed in conversion of n0 to n. So let us assume that the radioactive parent has produced d star atoms, number of atoms of stable daughter after time t. So n0 minus n will be equal to d star, because since decay of one parent atom produces one daughter atom, that's why d star will be equal to n0 minus n, or that is equal to n0 minus n0 e to the power minus lambda t, because we know that n is equal to n0 e to the power minus lambda t. So in place of n we have substituted its value, and finally we got d star to be equal to n into e to the power lambda t minus 1. This is equation 5. This is important equation. So the number of daughter elements produced is equal to n into e to the power lambda t minus 1. So if we take 1000 atoms of the parent, then after one half-life period, it will become reduced to, after one half-life period, it will reduce to 500. So daughter element is produced 500, parent is reduced from 1000 to 500. In next half-life period, the parent 500 parent elements will reduce to 250. This is 250, and the daughter element will become 750. So this is the curve for the daughter element d star, which is equal to n0 e to the power n0 d star is equal to n into e to the lambda t minus 1, or is equal to n0 into 1 minus e to the power minus lambda t. So this is the graph for the daughter element. This is the graph for parent element. N is equal to n0 e to the power minus lambda t. So on the abscissa, we have taken the half-life periods, number of half-life periods. Here on the ordinate, we have taken the number of atoms produced, both for parent and daughter, and we get two graphs, one for the daughter, the other for the parent. And they meet here in half-life, in first after one half-life period. So after one half-life period, n0 becomes 500, d star becomes 500. After second half-life period, n0 becomes 250, d star becomes 750. After third half-life period, n0 becomes 125, d star becomes 875. Like this it goes on. In nature, we cannot know the n0. What is its original amount, we cannot know. The number of atoms produced at the time of origin of the rock or mineral, that we cannot know. However, we can know the amount of stable daughter elements, that is d star, and the number of parent atoms remaining, n, in the rock after the time t, which is the geological time of the sample. So if we add these two, we can get the n0. So we have d star is equal to n0 minus n e to the power lambda t minus n is equal to n into e to the power lambda t minus 1. So the above equation, in the above equation, d star is equal to n into e to the power lambda t minus 1. It does not take into account the original daughter elements present in the sample. This d star is the product of radioactive decay. But there is a big possibility that in a sample, originally there might be the daughter elements in the sample. So therefore, this original D present in the rock has not been taken into account in the sample. D star represents the daughter element produced by radioactive decay. So there is this possibility that stable daughter elements was there in the sample at the time of the origin of the rock, and some daughter stable elements, atoms are produced by decay series. Hence, total daughter atoms, that is D, is equal to the daughter elements remaining originally present, that is D0, plus the number of daughter elements produced after time t, that is d star. So total d is equal to d0 plus d star. So d0 plus n into e to the lambda t minus 1. So this is the equation number 6. If we arrange this equation, d minus d0 is equal to n into e to the lambda t minus 1, and finally we get t is equal to 1 by lambda log e d minus d0 by n plus 1, or we can say it is equal to d star by n plus 1. So this is the age of the earth. This is the fundamental equation that we have already discussed, and this is the way how the age of the earth is being calculated by taking into account the number of daughter elements, the number of parent elements remaining. On that basis the age is calculated. That has been shown in this diagram. This is the age of the earth, birth of the earth, some time passed in formation of the crust of the earth, formation of the rock or mineral on the earth. After the formation of the rocks, the decay started. So this period is not known. So after some time, the rock types are produced and then the decay started. So this is the period in which the daughter elements have been produced. So here the parent atom was N0. It was having N0. And this line gives the daughter and parent element remaining. Now this shows the formation of D, which is equal to D0. This is D0. This is D0 here from D0 plus D star. So this is the region for formation of D. So D is equal to D0, which is original present in the rock, plus D star, which is the product of conversion of N0 to N. So N0 minus N is equal to D star. So this indicates the D, and D is equal to D0 plus N into e to the power lambda t minus N. So this is the fundamental equation, and this equation is the equation of a straight line. It is in form of y is equal to mx plus c, where m is the slope, y axis contains d or d0 plus d star, and x axis contains n, with d0 as c constant. M is equal to tan theta, which is equal to e to the power lambda t minus 1. So this equation is equation of a straight line. This is tan theta, this is c, this is m, this is x, mx plus c. So this is the equation, but d0 is the constant. This is the d0. Then this is the daughter element that has been produced from N0. So this is tan theta e to the lambda, and this is called as the isochron, that indicates the age of the rock. Age is equal to D is equal to here, this is the T, this is the T used for the determination of the age of the earth. So the age graph is a straight line. This is called isochrone. The age of the rocks or minerals is found out from tan theta. More the slope, more is the age. More the angle of theta, more is the age. When theta is equal to 0, it represents the origin of the rock or mineral, and hence birth of the radioactive element. Age is 0. And by taking into account n is equal to n0 e to the minus lambda t, we can find out the half-life, which is equal to 0.693 by lambda, by following the general procedure from n. So n represents the number of parent elements remaining, n0 is the original number of parent elements. After one half-life period, n becomes n0 by 2, first half-life period. T is one half-life period. So we get half is equal to e to the minus lambda into t half. And by solving, finally we get t half is equal to 0.693 by lambda. And this is the half-life period for radioactive element, where lambda is the decay constant. This is the fundamental equation. Thus, we can have at T0, n is equal to n0, at 1, T is equal to 1 half-life period, 1 half-life, then n becomes n0 by 2. When T becomes 2 half-lives, n becomes n0 by 4, that is equal to n0 into half to the power 2. After 3 half-life periods, n becomes n0 by 8, or it is 1 by 2 to the power 3 into n0. Thus, after n half-lives, n is equal to half to the power n into n0, or n0 into half to the power n. So n is equal to the number of half-life periods, and thus it is equal to total time passed by time period for one half-life. So this is the equation. In my next class, I will discuss on the values of half-life and the decay constants for some elements, their half-life periods, and how rubidium strontium are used in age determination. Thank you all for giving a patient hearing to my talk.